Section 4.1, linear growth. So we're moving into chapter 4 now. We're leaving behind probability. We left behind statistics. And we're going to look at growth in the linear sense and exponential sense. And altogether, this is kind of going to be our modeling section, so to speak. We're going to look at some linear and exponential models. Now, keep in mind, even though this class, of course, we don't go into the detail like you would in other classes into specific topics. But if you were to go on and do more work with the modeling concept, you would see that there are ties to both probability and statistics, especially statistics. You can collect data, plot the data, and then you can fit a graph to that data that has an equation. And if you can do that, then you can use that equation to maybe predict things in the future. So there are ties to the stuff we've done before. It's just we won't go deep enough into the modeling concept to get there. So overall, what we're going to look at here are the concepts of linear growth. I want you to understand that. And then the idea of being able to create a linear model and use it to solve problems. I want you to be able to do that. And that's going to be the bulk of what you're doing in this class, in this section, really. So linear growth, a quantity grows linearly if it grows by a constant amount for each unit of time. So one thing to keep in kind of consideration here is that it might not always be units of time that are changing. It might just be, a step, some sort of other value that's increasing. So it's for each unit of time or each step, you're going to see the amount overall or the quantity growing by a constant value. So, from one step to the next, and then the next step to the one after that, you're going to be seeing it grow by a constant amount, change by a constant amount. So, for example, consider a situation where you go to a gas station and purchase gas, snacks, and a drink. So if the gas costs $2.74 per gallon and you spend $7.52 on snacks and a drink, then the total amount spent would change depending on the amount of gallons you pumped. So let's take a look at this and think about if you pumped in 1 gallon, then the amount that you would spend would be $2.74 times 1. You'll see I'm going to change that number there as we move down. So that's why I'm writing it exclusively or explicitly, I should say, as a 1. But you have 1 gallon at $2.74 per gallon plus your snacks and drink charge. And now you have a total spent in this trip at $10.26. Well, if you go 2 gallons, the amount now is going to be 2.74 times 2. Price per gallon times 2 gallons will give you the total price for your gas. Then you add in the price for the other stuff, and you get a total of 13. For 3 gallons, you are now looking at 2.74 times 3 plus the 7.52, and that's going to give you $15.74 that you are now spending when you pump 3 gallons in and spend $7.52 on snacks and a drink. So for 4 gallons, similar pattern here. It's just you're going to put a 4 in the parentheses. And when you work this out, after you've added in your snacks and drink charge, you're going to have $18.48 that you spent. So the thing to keep in mind here, as the gallons increased, so this is, for each step, so to speak. So as the gallons increase, the amount changes by a constant $2.74. For each step you go, each 1 gallon that you add in, you are changing by $2.74. From this first price to the second, $2.74 difference. From this one to the next one, $2.74 difference. And from this one to this one, $2.74 difference. So you're changing by a constant $2.74. And that's what makes it linear. So a linear model overall is going to take that idea and just have a more general equation to it. So the linear growth model begins with an initial population called P naught, some starting amount, and then in each time period or generation T, up above, in each gas gallon you've pumped, the population or amount changes by a constant amount called the common difference D. So the basic model that we're going to use is P of T equals P naught plus T times D. So in the gas example, the price per gallon is the D, the common difference from one step to the next. And the cost of the snacks and the drink is going to be that initial amount that you're going to spend no matter how many gallons you pump. You're dead set on getting snacks and a drink. So you just say, look, I'm getting these. Maybe I can't pump gas today, but I'm getting snacks and a drink. So that's your initial starting amount. So overall, if you look at this, you have this P of T would then equal 7.52 for the P naught plus T times 2.74 if we wrote it explicitly in that form. And then T in this case is just the gallons of gas. So after you have that model, you can use it to help solve problems. So if you only had $20 to spend, how many gallons of gas could you get in addition to the snacks and drink? Like I said, you're walking out of there with those snacks and drink no matter what. So assume that the tax is included in the prices. So all you have to do is set this 20 equal to, because the 20 is the amount that you're looking to spend. You set it equal to the function rule on the other side, and you then start solving. So subtract 7.52 from each side. You get 12.48 equals T times 2.74. And then when you divide by 2.74, you get like 4.55 for T. And in this case, that's 4.55 gallons that you could pump in addition to buying those snacks and a drink. So if we take a look at this graphically, and I think it's important to see this to know why it's linear in a visual sense, you'll see what sort of graph is produced. So I'm going to go ahead and get this opened up here real quick. So you can see in this case, when you graph that model, and I just used X for T and Y for the P of T, you get a straight line. And that's why they call it a linear model, because it will always produce a straight line. And you can see here, your starting amount is going to be where it crosses the Y-axis, and then it keeps going up and up and up. And I think these go by twos here. So if you go right here, you could see, yep, there you go. So at 2 gallons pumped, we spent 13. And then you go up here to like, if I can get that to go almost. There we go. So at 4 gallons pumped, we spent $18.48. And you can just keep going up. And you notice that the first number in the parentheses just keeps growing. And then the second number is the amount you're going to spend based on the gallons pumped in the first number. So that's basically, what you will see with these linear models is a straight line every single time if you were to graph them. So let's go back over here and look at another example. So in this one, we have a small town, has a population of 12,000 people in 2018 and was increasing at a rate of 10%. So this one, a lot of times when you see percents, it's like, oh, you might be thinking that it's a exponential, but they don't say at a rate of 10% per year. They just say at a rate of 10%. So I kind of wish they wouldn't put this in here as confusion, but they do have that. So without the per year, for the percentage, then it is going to be a linear growth. So assuming that the population is growing in a linear fashion, so they're also going to tell you it's growing linearly. So there's a couple of clues. Use the information to create a linear model that can predict the population of the small town. Let T be the number of years after 2018. So what this means, and this is one thing you got to keep in mind with a lot of these problems in here, 2018 is when time starts. T equals 0 in 2018. So what we're going to do with this is first find, or set up, I should say, the equation, because I know I'm looking at linear growth. So I'm just going to get the equation written down. I recommend you do this so that you can get your mind wrapped around what you need. It's like, okay, the t, well, we're just going to have t be a predictive value, so we don't really need that right now. 2018 is t equals 0, but I'm not going to put a 0 in there. I want t so I can plug anything in to predict the population in future years. But I do see up here that the population initially was 12,000, so that's my p naught, increasing at a rate of 10%. So we got to do a little work to get d here. So the common difference will be 10% of that 12,000. And that's always what you got to do. If they give you a percent and it's like, well, how much am I growing? Well, you got to take that percent and multiply it, after you convert to a decimal, by the starting amount to actually get, in this case, the growth in terms of people is going to be 1,200 people per year. So with those two values, the p naught up here, the 1,200 for the d, I can set up a model, p of t equals 12,000 plus 1,200 t. I'm just going to write it in the normal way you write things with variables, variable being at the end. So now from this, we can go to part B, and it says use your model to predict when the population will reach 50,000 people. So when is a year? And this is where you got to be careful. I see this mistake all the time, because you're going to get a t and then you're going to answer with t. And it's like, well, t isn't a year, it's the actual number of years since 2018. So if you got like t equals 5, you didn't go back in time to year 5. You're actually 5 years in addition to 2018, which would be 2023. So keep that in mind when they say when. You're looking for a year and you need to add t to the original year to get that. Only if they say like how long did it take would you use the t as your answer. So moving forward then with this, 50,000 is the amount we want to see, the population after time. So that's going to be on the left side, and then we'll have 1,200 plus, or 12,000, sorry, plus 1,200 t. And we solve for t. So we'll subtract 1,200 over, or 12,000 over, sorry about that. And we get 38,000 equals 1,200 t. Divide by 1,200, you get 31.67 equals t, after we round a little there. So t is approximately 32. You're going to round to a whole number. And we don't stop there. Remember, we got to figure out the year. When did this happen? So 2018 plus 32 would then be 2050 is when we'd expect this population to reach 50,000 with that linear growth rate. So key thing, find t, then add it to the starting year that they give you to get when things happen. All right, let's go ahead and I'm going to stop video part 1 here, and then I'll do the last example in part 2, and then we'll be done with this one.